In the previous hour, I told you about some questions about interpolation theory for the Hardy space and related spaces. This talk is in that same spirit, but it's not about, it's taking what we know about the Hardy space and trying to see how it generalizes to other contexts. But now I want to talk about the spectrum of the multiplier algebras. So I will first remind you a bit about commutative Banach algebras, and then recall some classical results for the Banach algebra H infinity, which is the multiplier algebra of the Hardy space. Then I want to raise analogous questions for the multiplier algebra of the Banach space D sub alpha, these generalized Dirichlet spaces. The parameter alpha equals 1 gives you the Hardy space, and we're interested now in alpha less than 1. And greater than or equal to 0, alpha equals 0 is the Dirichlet space. The reason for this restriction in generality is, at this point, the questions are quite explicit and I can't answer them satisfactorily. So, excuse me. So it's a good enough place to start working. I'll give you some results that are positive, but at the end of it all, I have more questions than I do results. The basic idea is, in the presence of complete Nevelin pick kernels, a lot of the theory of the Hardy space extends in ways that, after you formulate things appropriately, look very similar to the classical results in the Hardy space. So, for example, the theorems of interpolating sequences for the space and for the multiplier algebra extend in rather natural ways to these other families of Hilbert spaces. And the question was, perhaps some of the classical theory about the maximal ideal space of the multiplier algebra of the Hardy space, which is fairly well developed, perhaps some of those results also extended. So I first want to tell you a little bit about commutative Banach algebras. Banach algebra B is a Banach space with a, for us, unital commutative multiplication. The characteristic property is that the norm of the product is nominated by the product of the norms, and the classical examples are continuous functions on the circle or any other compact Hausdorff space, or the algebra of bounded analytic functions on the disk, or any closed subalgebras of those. And that's enough examples to get into the spirit of what we're talking about. The basic Gelfand theory says that given any algebra like this, there is some compact Hausdorff space X, so that B is isomorphic to a subalgebra of continuous functions on X. The classically most richly studied case of this, one of the most richly studied, is when B has the additional property that, for example, H infinity has, that the norm of the square is the square of the norm. This property is always true for spaces of continuous functions on compact Hausdorff space with a sup norm. It's a characterization of spaces, an abstract characterization of the idea of having a sup norm. And when this statement is true, then in fact, not only is B isomorphic to a subalgebra, but it's isometrically isomorphic to a subalgebra of C of X. Our primary interest in these uniform algebras, unfortunately, is that the algebras we're looking at today do not have this property, so we lose some of the theory. Associated with any Banach algebra is something called the spectrum of Banach algebra, also known as the maximal ideal space. It's the space of multiplicative linear functionals given a certain topology. If you're not familiar with this, you should think of it as the space of bounded point evaluations together with generalized point evaluations. The generalized point evaluations are obtained by some limiting process and are generally not easy to specify completely or explicitly. Once you have this spectrum, the functions in the original Banach algebra, f, in the algebra B, are functions on the spectrum by taking the function f and saying its value at the linear functional A is the linear functional applied to f. So it's a almost tautological definition. And that topology, the topology on the spectrum makes all these functions continuous, and that essentially is the topology on the spectrum. Namely, you require those functions be continuous, and that gives you the topology. Now, even if X is relatively explicit and understandable, the spectrum can be very big. It can have a great deal of structure. It can be hard to understand. And in the example we're starting with as our motivating example, namely B is the algebra of bounded analytic functions on the disk, that's true. The spectrum has a great deal of structure, and it's hard to understand, and it's very large. If you start with the Hilbert space with reproducing kernels, there's a multiplier algebra, M of H. It's a Banach algebra with the operator norm. And classic Banach algebra theory tells you can learn about this Banach algebra by looking at the geometry or the topology or the function theory on its maximal ideal space, which is the spectrum M of H. If you specialize to the Hardy space, the multiplier algebra of the Hardy space is H infinity. The spectrum of H infinity has been very intensively studied from the 50s up to now. The classical theory is in the books by Huffman or the book by Garnett, and the classical theory goes back to the late 50s and the 60s. However, there's a great deal known since then, and it's an ongoing process. This map I mentioned that takes, forget that. The spectrum is a space of point evaluations. Evaluating at a point in the unit disk is a multiplicative linear functional in the algebra of bounded analytic functions, and that process lets you identify points in the disk with points in the maximal ideal space. When you write down all the definitions, what you end up with is a natural map of X in general for any multiplier algebra of a Hilbert. If you have a Hilbert space on X and you take its multiplier algebra and you take the spectrum, the points of X give you evaluation of points of X gives you multiplicative linear functionals on the multiplier algebra, and when you unpack all that, it gives you a mapping, a natural mapping that I'm calling phi sub nat of X into the spectrum. In other words, X is sitting inside the spectrum, and the point of the analysis is to find out what else is there. When you start with the Hardy space, you're mapping the disk into the spectrum. It gets mapped as a so-called analytic disk, which means that if I take which means that it's a non-constant map, and if I take any f in the original algebra and evaluate it at these points, phi natural of z, what I get is a holomorphic function of z. That's a lot of words. What it amounts to is saying if f is holomorphic on the disk, then f of z is a holomorphic function of z. We just went around in a circle. What's of interest, though, is, well, one second. What's of interest is those aren't the only analytic disks. And the other thing of interest is the analytic disks play an important role in the analysis. Because as soon as you see that you have this analytic disk in there, wrong. First of all, you can see H infinity as sitting inside continuous functions on the spectrum because functions in H infinity are continuous on that disk. And you can also, looking at that analytic disk, see these functions are analytic. And hence, H infinity is not the algebra of all continuous functions on the spectrum. Backing up a bit, the general point is the Banach algebra sits in continuous functions on the spectrum. The easiest to understand case is when it's the algebra of all continuous functions on the spectrum. The case where it's not is the case where you want to understand how it fails to be all of them. And that's where the analytic disks show up, because they're a part of the spectrum on which you don't get all continuous functions, you just seem to get analytic functions. So there's some analytic structure sitting in the spectrum in the sense that all the functions in the algebra are analytical in that structure, and that's an obstacle, an obstruction to getting all continuous functions on the spectrum. So these analytic disks are part of the answer to understanding how the space, the original algebra, fails to be the algebra of continuous functions on the spectrum. There's an obvious disk inside the spectrum of H infinity, the naturally included one, and this theory starts, this discussion starts with the fact there are other analytic disks. There are other ways to map the unit disk into the spectrum of H infinity in a non-trivial way so that the composite functions are analytic. And I will describe their existence in a moment and how you prove it, but wait a moment. So these general Banach algebras have a spectrum, and the spectrum carries a metric. The metric's the so-called Gleason metric, gamma. It says the distance between two multiplicative linear functionals, alpha and beta, is the supremum of the pseudo-hyperbolic distance of the multiplier applied to alpha and the multiplier applied to beta, or you take the supremum over all multipliers of norm 1. So this is certainly going to be at most 1. And in fact, saying that gamma is less than 1 gives you an equivalence relation on the maximal ideal space. And that's a consequence of the version of the triangle inequality satisfied by the pseudo-hyperbolic metric, which says that if you know the 2 points are, you have 3 points. The first 2 are at pseudo-hyperbolic distance less than 1. The second 2 also, then the first and third are also at distance less than 1. So that type of triangle inequality, stronger triangle inequality, extends to this gamma, so gamma less than 1 is an equivalence relation. The equivalence classes are the so-called parts or Gleason parts of the spectrum, and it's decomposition of the spectrum into pieces, and these pieces are interesting because that's where the analytic structure lives. More specifically, if you start with H infinity, then this naturally included disk is contained in a single part, and that's just the Schwarz-Pick lemma after you unpack everything. And in fact, any analytic disk in the spectrum is also contained in a single part, which comes from the Schwarz-Pick lemma after you unpack all the definitions. I mean, it sounds like a sophisticated statement, but it's fairly close to the surface when you unpack things. And the other thing we wanted to note is that NAG should be NAT. This natural mapping of X into the maximal ideal space, X already had a metric. It had the metric that came from the Hilbert space. It had the metric delta sub H. It now has this Gleason metric, gamma sub M of H. And they're the same. They're the same because that extremal problem I described earlier for multipliers. Given a multiplier of norm 1, maximize the pseudo-hyperbolic distance between two domain points, that extremal problem has an estimate. The estimate is sharp, and the extremal functions can be described. That's enough to get that gamma, the Gleason metric, is equal to this delta sub H, where they're both defined. So let me tell you what the classical theory is about the Hardy space. We defined an interpolating sequence last time. Let me call an interpolating sequence a member of IS. And it's an interpolating sequence for the multiplier algebra. It's automatically into bounded functions, so it's an interpolating sequence exactly if the restriction to Z is all bounded functions on Z. So examples, the sequence has to go to the boundary fast enough. 1 minus 2 to the minus n does go to the boundary fast enough. 1 minus n to the minus second power is a Blaschke sequence, so it's a 0 sequence for H infinity, but it doesn't go to the boundary fast enough to be an interpolating sequence. So there are 2 examples of 0 sequences. Only the second one is an interpolating sequence. And the way to think of these in general, it's all technical, but The basic idea is that it goes to the boundary fast enough. And the theorem was the sequence has to be separated. And the Carlson measure condition basically says the sequence is not too thick in any region in some very precise technical sense. And it's the theorem of I.J. Shark, 1961, that if you take an interpolating sequence, that's a sequence in the disk lives inside the maximal ideal space by this natural map. It's a sequence inside the maximal ideal space, which is a compact Hausdorff space. There are going to be accumulation points. Every one of those accumulation points is the center of an analytic disk, is a point where such that you can map the unit disk into the maximal ideal space, taking 0 to zeta in a non-trivial way. And we will prove that in a moment. And there's an interesting homework exercise to go find out who I.J. Shark is. And you can find that out by looking up the paper in Math Reviews. You find he didn't write a lot of papers. A wonderful theorem that at least answers all the first order questions of this type is 1967 by Ken Huffman. That says the Gleason parts in the spectrum of H infinity can be completely described. Some of them are singletons. The others of them are analytic disks, namely they are the one-to-one maps of the disk into the maximal ideal space such that every function in H infinity is analytical in that image. And that second case happens exactly when, if and only if, we're back where this theorem tells us it might happen, namely if and only if you're in the closure of some interpolating sequence. So in some sense, the interpolating sequences go to the boundary very quickly. Hence, their images inside the maximal ideal space, their accumulation points are buried rather deeply inside, but we don't want to try and push that discussion too far. So what do we know? The spectrum is really hard to picture. This naturally included disk is dense in the spectrum. That sounds like it might be tautological, but as soon as you go to unpack it, you find it's not at all tautological. And in fact, the statement that it's true is Carlson's corona theorem from 1962. The maximal disk contains the open unit disk by its natural inclusion. The rest of it consists of fibers over the boundary point, where a fiber over the boundary point is that statement z hat inverse e to the I theta means it's a place where the coordinate function, it's a place in the maximal ideal space where the coordinate function takes the value e to the I theta. So it's a bunch of point evaluations, generalized point evaluations, that give e to the I theta for the coordinate function. So it's a bunch of stuff sitting over that boundary point consisting of generalized limits. And that's where these analytic disks live. Each one lives in the fiber over a single boundary point. And those disks in the fibers each in turn have their own boundaries. And over each boundary point of them is a fiber which contains more disks. And it just goes on and on. I used to want to study these things, and I used to want to draw pictures of this, and it didn't go well. So over each point of the disk is a boundary point that has some fuzz of generalized limiting functionals, and they just smaller and smaller in infinite regression, one after another. And until yesterday, I thought we would be a little concerned about seeing a picture of this, but yesterday we saw pictures of a maximal ideal space, so we're much more comfortable with this. Here's what the maximal ideal space of H infinity looks like. So, a question that seemed natural after working with the interpolating sequence was this. Some parts of the classical Hardy space theory, when formulated properly, extend with great similarity to Dirichlet type spaces. I wanted to know if that was true for these statements about the maximal ideal space. They are Hilbert spaces with a reproducing kernel. They have the complete Nevelin-Pick property kernel, which means, among other things, that the Gleason metric on the spectrum agrees with the delta sub H metric. They each have a multiplier algebra. The multiplier algebra is a commutative Banach algebra. So we can start down this path. The spectrum is a compact Hausdorff space, also called the maximal ideal space, and that's the thing we want to study. And as before, all the elements in the multiplier algebra are functions on that space. So the multiplier algebra is some sort of set of functions on that compact Hausdorff space. Again, it is contained in, but not equal to, the set of all continuous functions on that compact Hausdorff space. And again, for the same reason, there's the unit disk is included in the spectrum, and all the functions in the multiplier algebra are analytic on that disk. And again, we're looking for analytic structure in the spectrum to help understand the difference, the ways in which the maximal ideal space is not just globally, but also locally fails to be all continuous functions on the maximal ideal space. I said, and again, there's a natural analytic disk that's part of the answer, the obvious part of the answer about analytic structure in the spectrum. And I mention it later, I think. That disk is dense in the entire spectrum. That's a corona theorem again, but now it's not due to Carlson. It's a more recent theorem, but the corona theorem is true in this case also. And the question is whether these algebras have a rich analytic structure. In specific, are there analytic disks inside the spectrum? Namely, are there images of the unit disk in the spectrum so that every function in the multiplier algebra restricts to those disks as an analytic function? They carry Gleason metrics. There's a natural map again, mapping the open unit disk into the spectrum, and the Gleason metric agrees on that image with the metric delta sub H that we defined previous hour. And that's again because the complete Nevel-Pick kernel gives an equality version of the Schwarz-Pick lemma. Again, gamma less than 1 is an equivalence relation. That's a general statement. And again, the equivalence classes are called parts. And again, any piece of analytic structure will be contained in a single part. So we're trying to close in on these pieces of analytic structure. So what we want to do is look at the Hardy space as a model and see what we can see. And the algebras we're looking at are these generalized Dirichlet, the multiplier algebras of these generalized Dirichlet spaces. There's the kernel function. For the immediate future, we make no use of the formula. But we can write down the distance formulas, the distances. The distance on the space d alpha and the space d1, which is the Hardy space, are comparable if both sides are small. And the relationship is a little more complicated if either the d alpha distance or the d1 distance is near 1, but you can write down something very explicit. The relationship when alpha equals 0 is more complicated, and also understanding what's going on here. At infinity in this case means off when delta is close to 1, and when delta is close to 1, maybe I should have written it the other way. You can rewrite this as 1 minus delta sub d alpha squared equals the other quantity to the power alpha. So there's some sort of snowflaking of the metric. The metric's being raised to a power between 0 and 1, and that's introducing some rather strong distortion that is increasingly apparent as you go out toward distance 1. So I said there's a corona theorem. Tolokonnikov proved it in 1980, and other people have, by modifying Carlson's proof, and other people have since found other approaches, but the naturally included disk is dense in the spectrum, and it's starting to look like the pictures are very much the same. The interpolating sequences are known for these algebras, and I pointed that out before, and again the condition is a separation condition and a Carlson measure condition, which says the interpolating sequence is just not too thick. But it's not quite the same as the Hardy space. If you're not in the Hardy space, namely if alpha is not 1, then the function theory is less well developed. The function theory on these generalized Dirichlet spaces is not nearly as well understood as the Hardy spaces. They are contained in the Hardy spaces, but the refined function theory is much more complicated. M of d alpha is not a uniform algebra. Partly because H infinity was considered so interesting, the theory of uniform algebras was developed very extensively in the 50s and 60s, and there are several different books with that title. The general theory of commutative Banach algebras is a little less well developed and less subtle, and as soon as we get away from alpha equals 1, we're back to this more general theory. The Carlson measure condition for interpolating sequences is completely explicit, but it's much harder to understand. The Carlson measure condition for the Hardy space says that a certain measure, that d mu z, is a Carlson measure, and you can then give the characteristic property that defines Carlson measures, or you can give the theorem that gives an intrinsic characterization. The same is true for these d alphas, but the intrinsic characterizations are more awkward. They're either capacitary conditions or testing conditions, neither of which are totally satisfying, neither of which are easy to work with. So, although the conditions are explicit, they're less well understood and harder to work with. When alpha equals 0, the Dirichlet space, the differences from the Hardy space are even more extreme. In particular, the Hardy space, a lot of the function theory is built around Blaschke products. That's not true for these d alpha spaces, but there are Blaschke products inside the d alpha spaces. There are some, and they are of use. By the time you get down to the Dirichlet space, there are no non-trivial Blaschke products. The only inner functions in the Dirichlet space are the finite Blaschke products. Also, by the time you get down to alpha equals 0, the geometry associated with this intrinsic metric has really changed quite fundamentally. For the Hardy space, this 1 minus 2 to the minus n is a separated sequence and is an interpolating sequence of the Hardy space. That's not true for the Dirichlet space. The kind of separation you need for the Dirichlet space is 1 minus 2 to the minus 2 to the n. So it's, in some sense, an order of growth going to the boundary in a faster order of growth in a way that's hard to put into words. But anyhow, there's a fundamentally different geometry, and that geometry is an obstacle to extending some of the Hardy space proofs in this context and others. Even when the results are known to extend, some of the proofs don't extend so well, exactly because this delta 0 metric in the large is so different from the pseudo-hyperbolic metric, which is delta 0, which is delta 1. So here's a theorem. Alpha is between 0 and 1. I take an interpolating sequence. I take an accumulation point in the interpolating sequence in the spectrum. And the conclusion is that zeta is the center of an analytic disk in the spectrum. And that's exactly the I.J.-Shark theorem. And it's true, and I was pleased with the theorem, but less pleased with it when I found out how to prove it, because you just take the old proof and you follow it line by line, and exactly the same proof works. So let me at least take the opportunity to tell you what that proof is. I have a sequence in the disk. I have an accumulation point in the spectrum. I want to find a mapping of the entire disk that goes into the spectrum and takes the origin to that point. Well, I take a Blaschke product with that 0 set. I look at the disk automorphisms that take 0 to z sub n. That set of automorphisms is a maps. Those automorphisms are maps into the spectrum. There's a limit map. It takes 0 to zeta. It takes the disk into the spectrum. By just normal families considerations, f hat of phi of z is going to be holomorphic. The only thing that's not trivial is showing this map is not constant. And I will show it's not constant by evaluating its derivative at 0. So I want to evaluate the derivative at 0. So the derivative of the limit is the limit of the derivatives. And I compute by the chain rule the derivative of the finite points. and I find I have to evaluate b prime at Zn and multiply by 1 minus mod Zn squared. And I'd like to know that limit is not 0, but the Carlson measure condition for the interpolating sequence, we have an interpolating sequence for this generalized Dirichlet space. That has to be an interpolating sequence for the multiplier algebra of the Hardy space just by inclusion of spaces. So this satisfies the classic Carlson condition. The classic Carlson condition says exactly that that quantity that we're taking the limit of is bounded away from 0. So the limit can't be 0. So the thing we want to be non-zero is non-zero, and we're done. That proof is fine, except when you stop and think about it for a second, I really needed b sub z to be in the multiplier algebra. And it's actually not clear at first glance that it is. Blaschke products are in the Hardy space, and Blaschke products are in H infinity just because they're bounded analytic functions. To get into the multiplier algebra of d alpha, you need more. And what's actually true here is a theorem that says if your sequence is an interpolating sequence for the multiplier algebra, then that Blaschke product is in the multiplier algebra. That's a non-trivial theorem that goes back to 1985 by Verbitsky. And his proof is quite classical. You can give more modern proofs, but you need something like this to make this proof work. The next theorem is a negative theorem. Not only doesn't this proof work when alpha equals 0, but it can't work when alpha equals 0. You can't have a theorem like that when alpha is 0. What does like that mean? We want to map into the maximal ideal space that has certain properties, so we take these maps from the disk into itself. They're marching off toward the boundary, and then we take a limit. And that's not going to work in the Dirichlet space. Here's a theorem. It says, well, there's a theorem. The theorem, the corollary of the theorem says the previous construction will only produce a constant map on the Dirichlet space. Because what the theorem says is if I take two accumulation points, the image of the origin, the image of some nearby point, and I look at the images in the spectrum under this limiting process, they collapse to the same point. So the general theorem says if I take points that are close to each other pseudo-hyperbolically, finite distance pseudo-hyperbolically just bounded away from 1, and I take a sequence of maps that takes these points to the boundary, then the delta 0 distance, the intrinsic distance on the Dirichlet space between those points goes to 0. If I take those disk automorphisms I was talking about, it doesn't change the pseudo-hyperbolic distance. So the pseudo-hyperbolic distance doesn't change. The fact that that distance doesn't change is what made the proof work in the Hardy space. The fact that it doesn't change means it has to be tending to 0 in the Dirichlet space, which means the two limit points are the same. The proof is a computational proof, surprisingly. I just want to show that under various hypotheses, this delta 0 Zn Wn tends to 0. So what I do is the delta 0 metric is sort of a mess, but you can get the first and second order Taylor approximation asymptotics fairly easily, and then you just draw some pictures and show that, and make some estimates, and it all works out at the end. So there's a theorem that's not we would have liked, but that's not true. So there are some things that are true, though, for the Dirichlet space. And in fact, the things that are true for the Dirichlet space, the proof I'm going to describe for the Dirichlet space also works for other spaces, but it gives you a weaker result than the one I stated. So this proof works for any Hilbert space with a reproducing kernel with a complete Neville and a pick kernel, and that domination condition. And I don't really know if the domination condition is necessary, but it is in force for all the d alpha below the Hardy space, and hence it was convenient since it was there to just use it. So this theorem also applies to all those other Dirichlet type spaces. It also applies to some spaces of functions in several variables, which again satisfy that domination condition. But again, the Hardy space itself, which is dA sub 1, and more generally the dA sub n spaces, are the model cases. They're also the endpoint cases in some sense, and they don't satisfy this domination condition. So the construction I'm going to describe doesn't work for those spaces. So the theorem is, if I'm in the closure of an interpolating sequence, then that Gleason part in the spectrum of the maximal ideal space contains some structure. I wanted an analytic disk. I'm going to get some structure. The structural outline will be a very unimpressive structure. I will prove it has at least 2 points. This proof can be souped up quite mechanically to give a countable set of points and some sort of metric information about how the points sit with respect to each other with regard to the Gleason metric. And I thought at one point I could get a continuous map of the entire disk, a one-to-one map of the disk into the maximal ideal space, but I lost interest in it because my construction absolutely wasn't going to give me any sort of holomorphy. What you'd like is to get a map in so that the functions in the multiplier algebra evaluated on that image disk would be holomorphic, and I don't know how to do that. So let me at least discuss the proof a little bit. I take a sequence of points that form an interpolating sequence. They're separated in the delta zero metric, so they've got some separation constant epsilon. And I pick C small enough depends on the fact that I'm in the Dirichlet space and depends on epsilon. And then I start following the pattern from before. I look at the point in the maximal ideal space that's an accumulation point for that interpolating sequence, an accumulation point not in the naturally included disk. And now I take some points W that are close to the Z's. And here's where I want to use that observation I made at the end of the previous lecture, that in the presence of the complete Nevelin-Pick kernel and in the further presence of that domination assumption, if I take WNs that are close in the delta zero metric to the ZNs, I will get a new interpolating sequence. So the W is a new interpolating sequence. Now, zeta is an accumulation point of the net Z. And now I look at the sequence W as I travel along that same net. It has an accumulation set inside the maximal ideal space. I call it omega. And I pick some little omega in that accumulation set. And I pass to a subnet along which the W's converge to omega. So now I have a subnet on which the W's converge to omega, the Z's converge to zeta, and I want to claim that those 2 points are in the same part and they are different points. So, as I said, the W's converge to omega, the ZN's converge to zeta. They're in the same part. Why are they in the same part? Because we picked them to be delta zero distance, not too far from each other. But the delta zero distance in the disk is the Gleason distance. So the Gleason distance between the W n and the Zn is not too far. But the omega and the zeta are accumulation points, so the Gleason distance between them is not too far apart. And where I wrote here delta zero, I should have written the Gleason distance. So the Gleason distance between omega and zeta is not too big, so they're in the same part. They are not the same point because the delta zero distance between omega and zeta can be estimated below in terms of the delta zero, Again, I want the Gleason distance here. I estimate from below in terms of the Gleason distance of the approaching points. That distance was set at epsilon over 10, so this distance is bounded away from 0. So they're not the same point. Let's see, we want to prove these things. The claim about limits follows from the definitions. So I want to see they're in the same part. And I do it by contradiction. We talked through that. I just talked through that. Why are they different points? I said that too fast. Why are they different points? I want to know that omega and zeta are different points because I showed before if we do things too casually, we end up getting everything collapsing to one point. So capital W is separated and satisfies the Carlson measure condition. So by the version of the interpolating sequence theorem we had before, it's also an interpolating sequence. Z is an interpolating sequence. They are both interpolating sequences. They are separated from each other by construction. Hence, their union is an interpolating sequence, because the union of two separated from each other interpolating sequences is an interpolating sequence, if I'm using this intrinsic metric. And hence, because the union is an interpolating sequence, I can find a multiplier that takes the value 1 on all the z's and 0 on all the w's. And hence, passing to the limit, m hat takes the value 1 at zeta, and m hat takes the value 0 at omega, and that gives you the 2 points are different from each other. So all this work got me 2 different points in the same Gleason part. What I would like is an analytic disk inside that Gleason part. This proof was an ad hoc, pick a point, pick some other things, and you got 2 points. You can certainly pump that up to get lots of points and some metric information about the points, but I don't know how to get analytic structure. On the other hand, it's not so clear what a proof would look like that there is no analytic structure out there in the maximal ideal space. Some of the things I was just saying extend to n variables where there is much less known about the maximal ideal spaces. Steve Krantz has a paper on the archive from not long ago about the maximal ideal space of the bounded analytic functions on the ball, but that again is trying to go back to the work from the 60s, 50s, 70s and see how it extends, and he's got some nice results. If you go back and look at the classical work on the Dirichlet, on the Hardy space, there's some very nice results. There's Ken Huffman's result that every part is either a point or a disk, and further facts. There's a very large literature about the spectrum of H infinity. What's the Shilov boundary? A theorem I like very much is that on H infinity, each fiber over a boundary point splits as 3 pieces, a left part, a middle part, and a right part. That sounds like it is formulated as a statement about the geometry, the topology of the maximal ideal space, but when you unpackage it, it's very much a function theoretic about the statement about the type of discontinuities bounded analytic functions can have on the boundary. So the books by Huffman and Garnett are nice places to find lots of interesting results about H infinity and hence lots of interesting questions about these things. But one thing that repeatedly gets in the way is these algebras are not uniform algebras, so some of the classical theory just isn't going to work. Well, that's all for now. Thanks.
Are there any questions or comments, please? I have a little question about the corona property for multiplier algebra. There is some results, some recent results about this, or it is clear, or what?
For these one-variable algebras, everything is known.
Huh?
For the one-variable algebras, everything is known.
Yeah.
In several variables.
You mean general reproducibility?
No, I mean for all these Dirichlet spaces.
Yeah, no.
In general.
Yeah.
There's a very nice theorem about solving d-bar equations with Carlson measure data where there are Carlson measures for the Dirichlet algebras. And then you can follow a classical proof. For general reproducing kernels, no. So the answer to your question is no.
Yeah. But there is some reduction to exactly some estimate of d-bar for this reproduction using curvature or something. No?
There's a proof structure. And if you have the d-bar solution, you can follow. But I don't know any place where the Carlson measures are well enough understood, except in these Dirichlet type of spaces. But I could be wrong. Yeah, the places where things are known is the places where there are descriptions of the Carlson measures that are good enough to use to prove a theorem of the form. If you have Carlson measured data, you can solve the d-bar equation.